Hello and welcome to this video where we do an example of the precise definition of a limit. The definition itself will not get reviewed that heavily, so if you have that in front of you, that would be great. So here the problem is to determine the limit of 2x minus 1 as x approaches 5. Well, that part should be easy, but then take that value that you determined for the limit and show that that actually is the limit using the precise definition. So here, the special x value a is 5. The function that we're taking the limit of, f of x, is 2x minus 1. F is a polynomial, and so f is continuous. And because f is continuous, by the definition of continuity, this limit should just be equal to plugging in this 5 right here. In Stewart and perhaps some other Calculus 1 books, the idea of doing this for a polynomial is called direct substitution property, but outside of the context of a Calc 1 class, people won't call it this. People would actually prefer this kind of argument of f is a polynomial, so f is continuous, and therefore the limit is equal to just to the value of the function. All right, so here L is equal to 9. So there's this first discovery phase. And it looks like this. You always just start with the final thing that you want. Plug in what you know, so f and f of x and L, just plug in those, and we can simplify this a bit. Now, when you have an inequality using absolute value, you can pull this apart into two separate inequalities, so we'll do that. The thing you're absolute valuing should be bigger than negative epsilon and smaller than positive epsilon. And then in both of these problems, you can add 10 on both sides, divide by 2 on both sides. And though we've solved for x, for what we need to do, it'll be more convenient to now subtract 5 on both sides. Then you can take these two inequalities here and combine them back into this form using absolute value. And now just recall the definition of the limit and just match things up here. And you can see that delta has to be epsilon over 2. Right? So we'll use delta is equal to epsilon over 2. We're done with this discovery phase. And so now here's the actual proof. Here's the presentation. So given an epsilon bigger than 0, we'll choose delta to be epsilon over 2. And then start with this. We're going to assume the part that appears with the if. And we'll explain this actually in the next slide, why we're doing this. But starting with this thing, what do we know? Well, we know that the absolute value of x minus, we're assuming this entire inequality is true, so we now know two facts. The first fact is that absolute value of x minus a is bigger than 0, and the other fact is that same thing is smaller than delta. So of these two facts, let's ignore the first fact. We're not going to use it here. And let's just remember the second fact. So we're distilling, in a sense, and just keeping the second fact and plug in what we know, right? We know that a is 5 and delta, well, we just determined previously to be epsilon over 2. And then you can take this inequality and, in a sense, work backwards from all the steps on the previous slide, or you can just work through these steps all again. Pick this thing apart, and you have this, add 5 to both sides, multiply by 2 on both sides, and subtract 10 on both sides, and then these two inequalities here can be combined just as we had done previously. And now you can actually try to take this and make this look more like absolute value f of x minus L. That's what we're after, just by doing this. So you regroup this minus 10 into minus 1, minus 9, and this in parentheses is actually the definition of f up here. So we'll replace that, and 9, by the way, was L. So just make those two replacements, and we've shown what we wanted to here. So what we've done is we've just proved the following, that if you start with this, then this is true, right? We've taken somebody who's skeptical and said, I don't buy the fact, this sentence, if blah, then blah, and said, all right, well, we'll convince you. So let's start with this for the sake of argument, and then convince the person who doubts that this is true. And this is the proof of that, this entire line of argument here. So just to take a step back again, it almost seems so unnecessary to do this, but it all lies in the fact that it's really if this thing, then the other. So just to talk about this just a little more, most theorems that we've seen are of the form if A then B, and for theorems there's really two different tasks. The main one that you're maybe more used to is using a theorem, or using really a statement that looks like this, right? And then the other is proving a theorem. So there's using a statement and proving a statement are really two different tasks. So what's using a statement like? Well, That's, somebody says to you, if A then B, and you believe it. Okay, you believe that somebody who says this, maybe because the word theorem is by it, maybe because it shows up in a textbook, maybe you heard it from class or something like that. So if you believe just the statement on its own, if A then B, then maybe in doing some math, you've discovered that A is true. And then because you believe this sentence, the entire sentence, if A then B, then you can conclude from this that B is true. And that's using a theorem or using a statement. But what we're doing right now is proving a statement instead. What does that look like? It looks more like this. You heard somebody say if A then B, but you doubt whether that's true, so you can try to convince yourself using a proof. And how does that work? To convince yourself that such a statement of the form if A then B is actually even true, what you do is you start by placing yourself in the hypothetical situation where A is true. Okay, so just A might not be true, but you just hypothetically start with, okay, A is true. And then from there, you do some work starting with A and, work on steps, do some math, add the same thing to both sides or whatever. And then you come to the conclusion that B is true. And so by doing that, by starting with just the assumptions that are in A, and then being able to conclude that B is true, you've convinced yourself that if A is true, then B would have to be true no matter what. And that's the point, right? So how this statement reads, the definition is that for every epsilon, yes, you have to pick a delta. But what you have to show is that if this thing is true, then this is true. So if I go back here, what we're doing is starting with if this, suppose you're in the situation where this is true, then this line of logic all follows, and then you've convinced yourself that this last thing is true.